Apparently, we like
Mine's
started
on.
20
Mine's on.
seconds ago. We had no idea. And just because I have this fancy mic, we decided to do karaoke instead. You know, who cares about slides? But you probably don't want to see hear
No,
me
you
sing,
don't want to
so-
hear us singing karaoke.
All right, so welcome to our talk, Just Enough String to Hang Ourselves. And to start with, we have a quiz for you. So the quiz is performance, of course. And who thinks the first version of a string concatenation is the fastest? Please raise hands.
Stand up.
Oh, stand up, yes, please.
Stand up.
Let's do an exercise, you know. It's
Yeah,
been
because
like,
it's so
please stand
comfortable
up.
here.
It's two comfortable chairs. You're going to fall asleep. So please stand up if you think the first version is the best. Good. We have a couple of people. Okay.
Oh,
5,
very
6.
good, very good.
All right. Version 2 with StringBuilder. You know, StringBuilder. Anybody StringBuilder? No? Okay. The same about amount of people. And the last one. We precise everything. We do exactly by the book.
Stand up.
Please stand up if you think it's version 3.
Okay.
If you haven't stand up to either 1 or 2 or 3, your brain doesn't work. We'll give away the answer later. And with that, I give away to Heinz.
All right, so we're going to look at Java from Java 1.0 up to Java 13.01. And in fact, we're going to look beyond that as well a bit. And Java 1.0, we had 3 fields in the Java class. We had, first of all, a char array, offset and length, and count. We'll see in a moment why we had that. We had some other weird stuff. For example, the bottom line doesn't show too well, does it? No, okay. So for example, the hash code used samples of the characters if the string was longer than 16. That's some other weird things like equals didn't actually check whether the objects were the same object. And in turn used a static hash table, which was a lovely memory leak. You could just, you know. Luckily, not many of us actually wrote Java. How many of you wrote Java 1.0 code? Like, for real? Okay, 1, 2 people in front. 2 poor souls. And because of that, they were awarded Java champion status. So, and string buffer was a modifiable thread-safe version. What was interesting about string buffer in those days, what they actually shared the underlying char array with string. So when you made it a string buffer, or a string from string buffer, it had the same underlying char array. And if you then change the string buffer afterwards, it made a copy internally. This is what the hash code looked like. And you can see, if you look very carefully, that if the length is less than 16, it went and added up all the different characters and did some magic calculation. And if it was more than 16 characters, it only looked at 8 of the characters. It didn't look at every 8th character, it only looked at 8. So it wasn't a very it wasn't a very good hash code in terms of, you know, getting very different strings giving the same hash code. And this is Dmitry Vyazelenko. Is that right? Something like that.
It's okay.
He's a principal consultant of Ingenious GmbH, and he's also the jQuery chief disorganizer. He really makes sure that we are as disorganized as possible. He does a good job of that.
And this is Heinz Kabutz, creator of Java Specialist Newsletter, Java Champion, the father of jQuery, yada, yada, yada.
Father, not
Father.
the mother. Okay, good.
Father. I said father.
So I've also have we have a little surprise for you. There's a little link. If you go there, you get something, but it's going to stop after 4:15. So only for now. After that, it's gone, right? tinyurl.com/GeeCON-SCZ-strings. I'm sorry that I added vowels in there, and it makes it more difficult in Czech Republic. So Java 1.1, they changed the fields. The fields stayed the same. Sorry, the fields stayed the same, but they changed a few things. For example, they changed the hash code. The hash code stayed the same as well. They moved the intern to native code. Now, moving intern to native code didn't necessarily make it faster than in Java 1.0. They also added some weird edge cases. For example, if you're in Germany, at the time, Unicode didn't have a character for uppercase SZ, that funny, thing that looked like a Greek beta. So they actually, when you called to uppercase, you ended up with 2 double S's, capital double S's, as a result. Java 1.2, they kept the fields still the same, but they changed the hash code. And even when Java 1.2 was released, there was already legacy code from Java 1.1 and 1.0. And people started complaining and saying, my tests don't work anymore. And people had persisted hash tables, and when they depersisted them, things were like blowing up. So they're very upset about that. But what they did with hash code, they changed it to looking at every character inside the string, not just 8 of the whole string. So we had bigger difference between similar strings, but we also had an order n string hash code calculation. And they also made string comparables instead of just having a special interface added in Java 1.2. Now, Java 1.0 and 1.1, the hash code wasn't very good, but it was constant time, order 1. Whereas 1.2, they changed it to linear time. Now, Java 1.2, for some reason, people liked Java in those days, without generics, without hotspot. They still liked it, and people started writing real production code with Java 1.1 and 1.2, and it wasn't very fast. So these guys wrote the Java Performance and Idiom guide. And I'm a bit short-sighted. Idiom guide, and the idiom guide, they had some good tips on performance. Now, the problem with performance is that it changes really quickly. So you're writing one thing, you're publishing it, and by the time your book is printed, everything's changed. One of the things that they spent a lot of time on, and they repeated it over and over again throughout the whole book, was that you should always cache hash codes. So if you, instead of having a string as a key, you'd wrap the string with another class, and then have the hash codes stored inside that class. Now, that was their proposal. It didn't really help that much for most cases, but they recommended that. And next version, the Java string internally cached the hash code. So that optimization idea didn't really help anymore from Java 1.3 onwards. And this is always the case with almost always the case with performance. You say one thing, and then you have to run around and try and tell everybody that, no, that's no longer true. So I live in Greece, and I've got this accountant who, he's a great guy, but he has a real problem because the government will make one law, and he'll tell everybody, all his customers who tell this law, well, not all, he'll tell some customers a new law, and then the next month they change the law, and then he has to try and remember who he told these things to try and change the law and say, hey, no, you can't do that, it's not illegal, then you must do something else. And it's a bit like that with performance. So this is why we asked that very first question, which one's the fastest, and we'll tell you the answer in a bit, but people have made up their own rules, or they write code differently depending on what they think is the fastest, because we all want to have the fastest code. So, so this is now the Java 1.3. They cache the hash code. And this also means that, strictly speaking, it's no longer immutable because the object changes. And there's actually a data race on hash code, but it's a benign data race. So if you have two threads calling hash code method at the same time, they might overwrite each other's hash code value, but it doesn't matter because the end result is the same. So it's who cares? Both times it's 42, right? Now, I met some people at the airport in Czech, Prague, and they gave me their names, so I wrote them down. You might recognize some of these guys. No, I'm joking. What do these strings have in common? What do you think?
Just shut out.
Hash code? Same hash code. Good guess, right? And in fact, they do have the same hash code, and the hash code is always hash code 0 for each one of these. How did I find them? Well, I actually found them with brute force, right? And you have to just basically keep on adding them together until you get back to 0. And the interesting thing about 0 is it's a special case. Is if I have two strings and the hash code is 0 and I append them together, the hash code is again 0 because you're multiplying 0 times 31, and that is equal to 0. So you can generate an arbitrary number of hash codes with hash code 0. And this way, it's really easy to generate an unlimited number of strings that all end up in the same bucket inside your hash table. Now let's see what happens when that occurs. So we've got a GitHub repository of their string performance, and there's a file here. Now I don't have Java 1.3 on my machine. This is not a Windows machine. But what I've got is I've got Java 6, which has the same behavior as Java 1.3 for this context. So the string DOS, what I do is I make a whole bunch of strings with the same hash code, all equal to 0, and then I see what happens to the hash table. So if you run the code with, this is now with Java 6, let me just do minus show version, and you see it's Java 6. And as I double the size, it becomes 4 times as slow to access. I'm doing a loop, and it's basically
Quadratic complexity.
Yeah, well, yes, absolutely. So the lookup itself is linear, but because I'm also increasing the number of roles, it becomes quadratic. So it becomes much worse. It does become 4 times slower or 2 times slower. Well, the actual lookup, if you double the length, it's going to take twice as long. So it's a linear lookup to find the elements, because of course they're all going in the same bucket. It's just a linked list, and that is not so good. And if you think nobody ever would have done this, well, yes, people have actually tried to attack Java servers by sending the same string off with hash code of 0. This wouldn't work if it's a different hash code. If it's a hash code of 42 or 1, then if you multiply that by 31, it's not the same number. So it's much more difficult to generate lots and lots of strings off a particular hash code, except for 0. So that's
the only thing you need to do is just send it in the HTTP header.
Absolutely.
Because the server would then create a hash map to parse the header, and then off you go. DDoS the server. Don't do it at home, sorry.
Well, we'll get back into this whole thing a bit later. So put and get both become linear. Java 1.4, the fields were the same as 1.3, but now they had another interface called char sequence. And char sequence abstracts over string, StringBuilder, and string buffer. No, actually, StringBuilder wasn't there yet. We'll get to that in a second. They also added regular expressions, which are very, very handy. Now, just before we carry on, in Java 1.4, when I added strings together, like hello plus arg0, what it actually did is it compiled the code to new string buffer dot append hello dot append the arg0.toString. So it generated that code for me on the fly. Well, when I compiled it. And when I made the new string buffer, it would always make an array of 16 chars. Didn't matter what was actually inside my strings. 1.5, they tried to solve a few problems. So the first problem they tried to solve is that that string buffer itself was synchronized. Now, we all know that synchronized methods are expensive to call, right? We know that? Who knows that synchronized methods are expensive to call? All right, good, because it's not actually true, but we all think that, right? We all think that. So string buffer, they wanted to have another class, which was StringBuilder, without synchronized methods. See, the problem with synchronized methods is that, well, you have to always get the lock. And most of the time when you're creating strings, the whole objects are stack confined, they're only inside the method. So you don't actually need to synchronize anything because it's not visible from outside. And so they made another class called StringBuilder, which didn't have any synchronization. I remember that they used to share the underlying char array between the string buffer and the string. Well, they couldn't do that anymore because it would either be string buffer or StringBuilder. They didn't know how to share that. So that changed a bit. They also added code points. And something that you needed to do in order to get this new StringBuilder without synchronization is you had to recompile all of your Java code. So, some people had already lost the original Java code. So you had to basically decompile it with JAD and then, change it back to plus and then, recompile it. It was a mess for a lot of people. And they couldn't take advantage of these new features. Java 1.6 didn't change much, but they did have for a while this experiment of compressing strings. And the idea with compressing strings, you could either have a char array or a byte array internally. Now, because it was made in America, they only supported US ASCII. So if it was even Latin 1, it wouldn't actually compress it. So it had to be just 7-bit US ASCII at the time. So that was the idea with compressed strings. They also optimize a string concatenation. So they actually managed to still share the underlying char array between StringBuilder, string buffer, and string. Even though, if you look at the bytecode, you can see that they make new ones, but they don't actually. It's actually all managed. Something else changed in 1.6, and that is that they added the ability to do escape analysis in the Sun JDK, and with that, lock eliding. And what that means is that all of the synchronized method calls that are unnecessary can be eliminated. So if the object is only visible within a stack, they can get rid of the synchronized. So they made one solution, specific solution for string, and in the next version of Java, they solved it in a general way. This often happens. You want to add anything?
Cool.
Cool. Now, we had this quiz at the beginning, and to be quite honest, the people who didn't stand up were the correct ones, because they're all exactly the same, right? There's no difference. And this has been the same since Java, well, at least Java 6, since we had optimized string concat, the answer was exactly the same. It didn't matter if it's Java 6, 7, 8, 9, 10, 11, 13.
If you append strings only.
That's the key. It was a trick question, like most of our questions are. And the trick here is that if you're appending strings together, strings are a special case. And for strings, it actually compiles down to the same. It's exactly the same. Now, you can see that there is a slight difference in performance and also the number of bytes. We'll get into that when we get to look at Java 9 and what's happened since Java 9. So all those people that insist that you have to use StringBuilder because it's faster, well, yeah, I guess it's not necessarily true. Then in Java 1.7, they changed a few things again. They changed the way that string is stored internally. In the past, we had an array, we had an offset and a length, a count. And they changed that to just be a pointer to the char array, which means it always started from 0 up to the length. So it changed a bit. They also added something else weird, which is a hash 32. This hash 32 was an alternative hashing function that would be used inside HashMap to avoid this problem, this DOS we saw before, the denial of service attack. So it was a slightly randomized hashing function which they could use to generate objects.
Can we see that? Did it work?
Yeah, absolutely. So what you do is you simply pop over to Java 7, and now when you run it, it's like super fast. So this is amazing. Look at this. It's like okay. Well, okay. Maybe it's not that much faster. So I spoke about this quite often, and I mentioned, yeah, this cool thing, H32. And when we were preparing for this talk last year, we went to Java 1 last year, and we spoke about this. And whilst preparing for the talk, I realized I tried it out, and it didn't actually work. And what I realized is that you have to specifically turn it on. So there's a switch here that says -d JDK map alt hashing threshold equals whatever number it is, and then it starts using this other mechanism once you get to that level. So
after that length of map, right? After that number of elements.
Yeah, something like that. It's like something related to the bucket size. I'm not sure exactly if it's the number of buckets or the size of the number of elements. But you can see it starts at about the same speed, and once it gets beyond a certain size, it's like, whoa, look how fast this thing is. Like 1 millisecond instead of like 200 milliseconds. So it's much better, right? Much better. Except you have to turn it on. I didn't know about that. I was like, hey, cool, look at this cool new stuff. But it didn't actually work. So this is another example where we see a very specific solution to a specific problem for string, right? So they solve that. Another problem that we had is, well, a problem, a change, an opportunity for consulting, is that they changed the internals of string. So in the past, if I made a substring let's say I made 1,000 substrings of one string, it would have 1,000 objects, very lightweight, pointed to the same char array. Whereas now, if I make 1,000 substrings of a string, that would make 1,000 time char arrays for each of those strings. So you could create far more objects than before. And of course, the reason why is because people didn't actually understand that if you make a substring, it doesn't actually make a new char array. And so people would end up with memory leaks because they didn't know what they were doing. So they fixed it this way.
But Java is not the only runtime, right? V8 had the same. They
Oh, it also did
they
this.
started with substring sharing array, then they removed it because it's memory leak, and then people would complain that the benchmarks are bad, so they would put it back.
Oh, they put it back. Well, they
At
didn't
least,
put it
at
back.
least in Java, they didn't put it back. Yeah. So the primary reason is the memory leak. So if you have 1 GB big XML and you get 5 characters out of it, well, you retain 5 gig, and now you have 5 characters. That's the reason why.
Like you could, of course, just make a new string, and then
Yeah, of course.
people don't know that. Some other weird feature was there was this way that you could make a string from an existing char array with a class called shared secrets. Now, you know programmers, if you call a class shared secrets, they're going to go like, I'm going to check that out when I go home. I want to use that. It's like, no, it's actually not for you to use. I'm going to use that, right? Shared secrets. It's like unsafe. Everybody wants to, I want to use that. You know? I want to go off heap. I mean, you can't even get the normal coding right, but you want to go off heap. You know, come on. This mechanism doesn't work since Java 9. Fortunately, it's gone. But it was there. Java 7 and 8, you could actually make new strings with an existing array. So I showed you this already, the string DOS. Java 8, they got rid of the hash 32, and they solved the problem in a general fashion, right? So instead of having, once you have a lot of collisions inside one bucket inside a hash map, they build up a binary tree, like a red-black tree in that position, which makes it easier so that you don't get the same type of degradation of performance as the table grows. So if I run the same demo as we had before, just with Java 8, oopsie, 87, it's not yet, soon. You can see that, okay, you don't need that flag anymore. As the size doubles, it does get a bit slower, but not at the same level as it used to do. So this is obviously much better.
But I want my 2 milliseconds back. Bring back the hash 32.
No, okay. But I mean, if you have you must be punished a bit if you have dumb data like that, right? There's got to be some punishment.
So they basically now solve the problem on the level of container, right? The hash map is now protected against the attack, not the particular key.
Yes, but there's a catch, right? For string it works fine, but for other classes, for other types of keys, you really need to make your keys to be comparable to protect yourself fully against this. They've also got a bunch of static methods. They also have deduplication of char array. Now, that's something which is pretty cool, because normally if I make 2 strings, which have the same basic content, it's actually going to make 2 copies of the char array. So here, for example, I've got my name twice, but as char array, so it makes a copy of those. And the problem is, when I make the copies, I've got 2 times the same char array lying around. What they did was for G1 specifically, they have the option of deduplicating the contents of the string. So if I look at the before GC, you can see that these are 2 different char arrays. And after GC, it's pointed to the same char array. So one of the char arrays, it's thrown away, it's garbage collected that, and the other one, it's kept. So it's sharing that. This happens transparently. You have to turn it on explicitly, and it's only for G1. The reason why I have to turn it on explicitly is whilst it does save memory, and in some cases it's like 30–40% of memory is going down, it does cost something in terms of performance. So you have to be able to disable it if you don't want it, or enable it if you want it. Now, there are different ways you could do this type of sharing. One is deduplication, which happens automatically. Another one is to explicitly call intern. And I've seen classes, I've seen projects where the number one bottleneck in their whole application was the call to intern, right? Now, when you call intern, it actually has a look at the string table to see if that object already exists inside the string table. If it's there already, it gets it from there, and you have it. But it's a native method call every single time you call it. Plus, when you call it, the first time, if the object doesn't exist, it puts it in. So this string table will grow indefinitely until, well, depending on the Java version. Like on some Java versions, it's going to keep on growing until you get a full GC. And then it will collect it. the more modern Java versions, so Java 13, for example, it actually collects it before, it collects it in young space. But in the old, like before Java 13, is anybody using Java 13 in production? Besides Josh and myself, probably nobody. It's like, you'd be happy to be on Java 8, right? But if you're on before Java 13, you're going to be paying a full GC when you're running out of intern space, which is, of course, a lot more expensive than the partial GC. This is with G1 GC. So
And the default size was like 1039 before Java 9, right? It was
yeah,
ridiculously small.
I think it's Java 6. So Java 6 was like 1009, the hash table for strings, and then they changed it to about 60,000 in Java 7, I think, and then and since Java 12, I think, they've made it that it's actually flexible, can increase in size, but it's still a system call, and it's going to cost quite a lot to call it. So another way to do this interning is to have your own concurrent hash map. This, of course, won't ever collect the strings. So if you've got lots of duplicate strings, which you can control, that's not a bad option as a sharing, or occasionally clear it out completely. That might not be a bad option. All right, I showed that already. Don't say so.
Okay, so with that, we concluded Java 8 and historical, and everybody, who's cool, uses Java 9, right? 10, 11, 12, 13, no. All right, so if you ever gonna migrate from Java 8, and this is a big if, right? You're gonna get this picture. So the fields changed, and the fields changed in a dramatic way. Our character array that we used to have for 8 versions of Java disappeared. And instead, we have a byte array and decoder. So if you recall, back in Java 6, we had the attempts to do the compression of a string. Well, it's no longer an optional feature. It's actually a feature of the VM. So the strings are compressed. And what is compressed? As long as your string can fit in 1 byte, means like Latin 1 encoding, so US ASCII included, plus a bit more stuff, like German, it can be compressed. If not, the character will take 2 bytes in the array, and the coder defines what it is, and then we have a hash field. Then we have yet another feature, which is also big in strings, and it's actually a change to string concatenation. If you recall before, the string concatenation was implemented as a sugar by Java-C by creating a string buffer until Java 4 and StringBuilder from Java 5 onwards, which means that if you want to optimize it, if you work on VM, you have no chance but to do a change to Java-C and ask everybody to recompile their code, which sort of sucks. JDK and Hotspot, in particular C2, had some special optimizations for certain parts of concatenation, like concatenating integer would be fast, but if you concatenate long, it would be slow, because there was no special pass down the line. So they decided to do it differently. And since JDK 9+, we have a concatenation done via invokedynamic. So just to see what it actually all brings together, so if you now do the string benchmark and concatenating stuff together, not just strings, but mixed parameters, like add a string, plus an int, plus a float, plus a long, plus a boolean, stuff like that. And then you run different benchmarks, like you use normal plus, you use StringBuilder, you size StringBuilder, like in the first question, so first 3 are the same. Then you use the method string concat. It exists in Java since a very long time ago. And then you do the format. You see that across the versions, universally, it was basically StringBuilder size that was the fastest across the versions, until 11.
And use the less memory. It allocated the least bytes.
It was the best.
It was really the way to code if you were the cool guy.
But look what happened in, well, it's basically 9+ is the same. So now all of a sudden, the plus is the fastest and allocates 152 bytes. If you actually look at our benchmark, 152 bytes is exactly the number of bytes needed to create the string. So it doesn't waste a single byte, which is cool, huh? And the rest is basically just down the drain because they don't have the optimization. So okay, so how does it work? JEP 280, Indify String Concat. As I said, the biggest problem, string concatenation shape was backed in by compiler. Let's change that. So since Java 7, we have invokedynamic, which means super cool invocation mode where the target, what you're invoking, is not known at the invocation time, at the compile time. So at runtime, you have to resolve it. So they basically, it's like anything in engineering, have another layer of indirection solves the problem. That's exactly what they do. So when you compile your plus code, what you're going to see a single invokedynamic call, which will jump to string concat factory, which will actually at runtime will build the code to run this particular concat. So every single concatenation in your code becomes a custom code generated at runtime. How cool is that? And then you have 6 strategies. So one is the bytecode generator that uses StringBuilder under the hood, and another one using method handle combinators. And the default strategy is called MH inline sized exact. What it stands for is that it stands for method handle based byte array directly inlined into string strategy. So whenever you do the concatenation, what you have a byte array allocated, and you allocate directly into the array. So there is not a single object created during the process, and then this byte array is dropped into a string in a shared way that's not available to us. So the package private constructor in the java.lang class, where they can actually assign array to this thing. So if you run and you compare different strategies, you will see that this wins. So default strategy wins. I don't even know why we have different strategies to begin with.
Well, why do you have different beers, right?
Yeah, probably someone would want to run some experiments. I don't know, but basically this is the default, and this is what it means that if you want to get this feature, you need to recompile once again. Ever since you update to JDK 9, you recompile your source code, but once. And ever since that day, the string concatenation would be fast and optimized further without you need to recompile.
Yeah.
But recompile once you need.
Yeah, not just that. You need to throw away all that StringBuilder code you've written.
That's
and replace it with plus.
Well, not really. So if we want to talk about StringBuilder, there are some use cases for StringBuilder. So for instance, if you are concatenating in the loop and using something like a plus equal 1 plus 5 string, it will allocate on every iteration of the loop, and it will create a new string. So if that's most likely not what you want, so you would want to have a StringBuilder allocated before. So StringBuilder is not that bad. There are use cases for both, but if you just concatenate a couple of things, use plus. Now, compact strings. This is a cool feature. We can save memory, right? Heinz mentioned 30–40%. Depends on the heap. Depends what you do with your strings. So
with
if you have lots of
deduplication.
yes, but that should also kind of bring us on 10–15%.
Maybe more.
Some maybe more. Who knows?
Yeah.
Depends how many strings you have in your application. So compact strings. Instead of character array, we have byte array. If strings are compressible, they will be stored as 1 byte instead of 2 bytes. You have a kill switch. You can turn it off. Everything's nice. 2 particularly interesting failure modes. One is maximum size of the array. So in Java, you can allocate array of max integer -2. So that's as many slots as you can have in an array. While before, you could create a string with as many characters. And if this string is also Latin 1 string in the JDK 9+, it will still work. Your code will compile and run. If your string was UTF-8 string or had at least 1 UTF-8 character in it, the code will crash with out-of-memory error in JDK 9+. Because your array is just half the size that's possible, because you need 2 slots in the array, so array is just basically half of it. You'll have nice out-of-memory error saying maximum size of a string is 1 billion elements in the byte array. And another one is every time when a string is constructed and compact strings are enabled, it tries to compress on the fly. So if you recall, all the API that we have is backward compatible. As we heard today, that's a mantra in Java world, everything must be backward compatible. So if you create a string from the character array, it will try to compress it. So it means it will allocate a byte array and start copying characters as single bytes. And if along the way it determines non-compressible character, it has to throw away the byte array, create a new one, and keep going. So if your application uses lots of UTF-8 code, or UTF-8, or any strings that don't compress, so basically non-Latin 1 characters, you will have a performance hit, because this thing will be allocating garbage every time you call. Therefore, you have a kill switch.
So any check characters with the thing like that on top is going to cost you extra.
Yes, but in general, it's a cool feature.
Well, yeah,
Yeah.
in some countries.
And it's funny because you also have like a kill switch, and Alexei Shipelev has an entire talk about, half of the talk is how to implement a kill switch, which is a string property on a string class in the JDK. There's a little bit of chicken and egg problem, simply because, and they couldn't even use unsafe. So what they did eventually, you see in the code, you have like private static final constant defined with a value, but not treated as constants by Java-C or VM, because VM on startup will overwrite it. So they had to do a backdoor in the VM to implement it, because, well, obviously you need the kill switch. So we did some more benchmarking, how the compact strings affect things. Well, actually, if you have compact strings, you allocate less bytes, because strings are, in this particular case, compressible. You allocate more bytes, it costs you performance, because you have to copy more, move more. So it's a win when you can have it.
It's amazing how bad format is, string format. Don't ever use string format, right?
That's another thing.
It's
By the way,
like
this is something that is the best from usability point of view, API-wise, so something like string format, but it's horrible. And it's horrible for a very simple reason, because you provide a format string and you provide parameters. Format string needs to be parsed upon every invocation, because there is no object that holds the state, so it has to be parsed. All the arguments to that method needs to be boxed, because it's defined as object array vararg, and an array needs to be created. So it allocates the most garbage, and yeah, who would ever use string format?
Stupid.
Not yet. Okay, so what else happened? Well, obviously equals and hash code and everything had to change. And interesting bit is here. They added a new if statement, checking the coder. They observe if you have compressed and non-compressed strings, they by definition cannot be equal. So you can short circuit and exit early. So only if coder is the same, you continue equals, otherwise not. And we looked inside, so how equals is implemented, it's simply walking the array, right? That's what we thought. And then we copied the code and ran the results, and somehow it didn't add up, right, Heinz? So we kind of look at stuff, at small strings, it did make sense, and then the bigger the strings, somehow didn't work.
There's some really weird magic going on, the fact that you write the code and it runs, but it doesn't run as fast as what Java wrote.
Who knows why? Is it because I copied the code equals into my own namespace? Maybe java.lang is the magic? Anybody can spot something magic on the screen, maybe?
Yeah,
annotation, hotspot, intrinsic candidate. Do you think if I put that in my code, it will be fast? No. No. There's hotspot intrinsic candidate says that inside a hotspot, certain codes or certain methods are implemented as native code. If it's available on a particular platform, it's also platform dependent, nicely. So sometimes this code will be executed on some platforms. On some other platforms, there will be generated machine assembly code, which in this particular case is fast as that, because they walk, instead of walking byte by byte, they walk in strides of 8 bytes at a time. So simply walk memory faster, in more predictable way. So here we go. And now we're at Java 13. Actually, we did this last talk 3 weeks ago, 4 weeks ago in Tallinn.
Estonia.
And we were like, nothing to update. You know, Java 13 came out, they didn't change string, and it turned out they did. Actually, if you look closely, there is something very interesting, which is hash is 0. And hash is 0, if you recall before, we would cache the hash computation, but if the hash code would be 0, you have to recalculate again and again and again, because 0 was the default value.
Can I pop back to the code quickly?
Yeah, sure.
It was this one.
Yes. So as you see here, we check if hash code is 0, and then we keep computing. So in cases of DDoS attacks, that Heinz used this hash code 0 stuff, there's yet another thing that will prevent it from happening, because this thing will not, well, it will not prevent the DDoS attack, because thing will end up in the same bucket on the older version, but at least the hash code computation will not cause a performance problem anymore.
Yeah, it's very easy to generate an extremely long string with hash code of 0.
Can you get back to 13, please?
Oh,
Cool.
Sorry.
Okay, so what else happened? As I said, they prevented hashcode zero computation. We have this ongoing stuff. So in Java 12, they wanted to have raw string literals. It was in some preview builds of Java 12, and before Java 12 was released, they pulled it out. Now finally we have text blocks, so everybody wants raw strings in Java, right? So you'll be able to like 3 double quotes and then write your SQL or HTML directly. Super cool. We have now preview feature. Interestingly enough, preview feature brings some API. I cannot point here, but I can point here. Some API like these 3 new methods. And the newly methods are annotated for removal at the day they were introduced, which is cool, right? They're deprecated for removal, so please use this code carefully. Well, actually, yeah, it's a preview feature, so you probably don't want. So what it allows us to do, it allows us to do something like this. You have HTML string, and HTML2 is using the text blocks, no concatenation in between, everything nicely, except of closing quotes are significant. The position of them defines how much empty space at the beginning will be stripped or not. So it's quite interesting. There is a link to text blocks guide by Stuart Marks and
It's by him, but it's surprisingly complex.
Yes, and it's
a lot of edge cases.
I don't know if it will survive until 14, but we'll see. Something like that is cooking in Java. So we thought about string format before, and actually the problem is usability. Like if you see on the screen here, we have append basic, we have lots of spaces, and then what if you use basically like format? And I said before the problem with format was you have to parse the string every time, you have to box the arguments, you have to create an array, yada yada. Well, there is a solution coming in Project Amber, and this is JEPS 348 compiler Intrinsics. They want to solve it again in generic fashion. So what if we take the idea of string concat with invokedynamic and bring it to other operations? Let's say string format is one candidate. Can we use invokedynamic there? What about objects hashcode? Objects hashcode has exactly the same problem. There is a dynamic array, var args, same issue with primitives and stuff. Well, if you take a Project Amber master branch, and then when you compile, you run with specific flag, in this particular case, -xd intrinsify all, it will enable this optimization that will intrinsify replace with intrinsics basically, use invokedynamic for stuff like string format. And if you see, back in JDK 11, it's 2000 nanoseconds, back in Amber 61 nanoseconds, exactly like plus. Because at the end, it basically uses the same code under the hood. So eventually in Java 53, or at least when I will be 53 years old, I think we will get the Amber branch ready, and we could write string format and use nice code idioms.
The reason the numbers are quite different to the other ones is because we lost the other laptop we were running the tests on, and this is a new laptop. So
yeah, that's another thing.
We'll have to redo all the numbers at some point.
Yeah, on Amazon, right?
It's a lot better.
You want to conclude?
Conclude. No, you carry on. You're doing a good job.
Cool. Lessons learned. Concatenate using string format.
Yeah, it's slow now, but
yes.
It'll get faster later, and it makes the code a lot more readable.
Well, yes, it's like you can write future-proof code if you use string format. At some version of Java, it will be fast. By the time you will be fired or switch 3-4 jobs, it doesn't matter. You left some legacy behind. No, there might be time when your string format will be okay, or if it's not performance critical. If you format exception messages and the exception happens once in a blue moon, it's fine. And if you do use concatenation in performance critical code, use either plus or StringBuilder if you are located in a loop and bigger quantities. Avoid intern at all costs. If you need the duplication, write your own.
It's always the balance between developer cycles and CPU cycles. And most of the time, we really care about maintaining the code and people being able to read it well and so on. And so string format, even though it's actually a lot slower, it's like 20 times slower now, it still makes sense in many cases. I use it a lot, string format, because it's just easier to read.
Yeah, maybe it's fine. In your courses.
No,
But it's in production. You know?
no, in production, most of the time, your bottleneck is not going to be on generating a string. It's going to be on
It will be string
database.
intern
it's a database.
after the format.
Right, exactly. That's it. String intern after the format.
Yes, and beware of compact strings. You might see some benefits. You might hit some gotchas, like non-compacting strings and some out of memories unexpectedly. Good.
So we've got another 4 minutes for questions. I don't have the app here. I didn't really have the app.
Questions? Do you have a
Slider.
URL? Do you have a URL?
A euro?
You can go to URL.
Euro.
Euro. Yeah, give me a
I
euro.
don't know, euro.
Every time you say don't have an app, I should get a euro.
Yeah, that's a good idea. So,
In the speaker guide, they had
that's Slido, isn't it? But I don't have it on here.
yeah, slido.com. No, go to .com. Slido.com.
Slido.com.
Yeah. But yeah.
Slido.com. Oh, that's the same one.
And put in GeeCON 2019, and then you select. Now the problem is this is not the wall. You need another URL because you will be
Okay. It's not going to work from my side.
Yeah.
Does anybody have
Anybody have live questions? We don't have access.
just
to the
shout
app.
them out. We'll repeat them on the microphone.
Okay,
Besides,
no
can we please go for coffee? I think that's the only one.
Yeah. If you're standing between you and coffee, so
We'll
it's-
be here
it's clear.
today and tomorrow. That's again the URL, the link with the special thing that you're going to get. Ah, good a question. Excellent.
Josh, go.
Oh, if you haven't gone to the URL, you should. There's URL. Well, I'm not telling you. But if you're watching the recording, you're not going to get as cool as stuff if you go there now. It changes after 4:15.
It expires, right?
Yeah, it changes magically. So change is good.
Okay.
So thank you
Thanks
very
for
much
coming.
for listening.